think that you are standing close to the street and a car is moving in that direction from left to right and from right to left. And this car has some sound in it and spread signals around until it comes to your ear. Since the car is moving, because of the movement, the signals, the sound, the frequencies will be like this. This means that what you hear before the car comes to this, the closest point to you, the frequency that you hear is actually affected by the velocity of the car. When it gets closer to you, you hear higher frequencies. For example, if it is receiver frequency of the source, the frequency that you receive here is higher than the frequency that what happened when the car is here? Car is here and moving away from you. So again, you see that it is here like this, but the frequency you receive here, as you see here, the distance, the frequencies are, lower. So FR will be lower than the source frequency. But in reality, the frequency of the source is constant. Actually, it's the movement. When the source is getting closer to you and get far from you, it causes some changes in frequency. So let me draw another figure. So if we have the frequency, reference frequency like that, if then the car is far from us and getting closer, the frequency starts going down up to the closest point here, and thereafter when the car leaves us, the frequency goes down. It means that what I hear here before is higher and then get lower, so that's frequencies. This frequency difference is called for Doppler shift. Shift in what? Shift in frequency. And shift due to what? Shift is due to the movement. Due to the movement of the source to the receiver. That's the main principle of the Doppler shift. If you determine this frequency, you can somehow determine the distance, your distance to the source. That's the point. FR is the received frequency. Frequency of the source is 1 minus velocity of the source cosine theta over 1 minus velocity of light square. That's the principle. That's the formula between the received and the source frequency. So if we have a coordinate system like this, so you have X here, Y here, and Z here, and I have a satellite moving in that direction. And this is the vector of the velocity. And I have a point at the surface of the Earth here, P. This satellite has its own position, or a source has its own position. And what I need is actually this position. And what I may need to know is this R. Theta is this angle, the angle between the vector and this line, which is passing through P and S. So velocity is the velocity of the source which is moving. C is the speed of light. if we have a source moving from left to right, and this is the velocity of the source, and I am here, I have a receiver here, and this is the distance that I have. So, and this one will be the angle. Think of the velocity is this green vector. And if I project this velocity to this direction, which is this, then this will be V cosine theta. Cosine theta, but since it is in the opposite direction, then this is a minus. So then what does it say? It say that these are the changes, is this one, or this projection of the velocity, is actually showing us the changes of R with the time. Satellite is moving in the right position, that position, and it comes here, for example. This will be the velocity, and this will be the theta, and again, I will have the effect of this movement. In fact, these changes that I see here are the derivative or the rate of changes of the radial distance. Then I can write simply this, as these are the rate of the change. In that case, and C is too big comparing to the always, then I can somehow ignore this term, and I have to simplify this like this. Instead of minus V over C, I can write plus R dot over C. That will be the equation, main equation for the Doppler. This R dot is in fact D. Now the question is how to determine this range. So dr, if you look at this formula again, FR, F plus it. Then if this goes to the side, it's FR minus. Then I can write that, okay, R is integral from Ti and T1 and T2, which is in fact this position of the first position of the satellite and second position of the satellite. So then it will call it Doppler count, which is let's say 1 or 2 is Fg, which is actually the frequency that which is generating inside the receiver. Inside the receiver, almost the source frequency, not the source frequency. The source frequency is the frequency that the satellite has, and Fr is this frequency that the receiver receives. This comes. What does it mean? If I have a receiver here and I have a moving satellite from position 1 up to position 2, and they send signals continuously to the receiver during the T1 and T2, then I receive this FR, and then Fg is generated inside this receiver itself. And the difference between this frequency actually and the received frequency, which is Doppler bit frequency of the Doppler, the shift from this generated frequency is integrated over time. That's up to here, and this integrated result is called integrated Doppler count.